this week's workshop is on recommender systems, just like the previous one, but this one I will be morely focused on collaborative filtering, and that too not a trivial collaborative filtering, but using some deep learning techniques. So for this demo, basically I have focused on a paper called Neural Collaborative Filtering, and it's mentioned in the references link as well. So, and if when I proceed with the demo, you will just observe that it is an item-based collaborative filtering. That is, we have used ratings as a parameter as well to recommend um, basically movies to users. So this is mostly a movie recommendation system like that you see on Amazon Prime or on Netflix, something on those lines. So let me just quickly switch on to the notebook and let's get started. So this one is actually a pretty simple but yet an interesting idea. So if you would have read about collaborative filtering, which is quite a famous recommendation technique, it basically relies on the mathematics of matrix factorization. So in this paper that is over here, the neural collaborative filtering, we have, if you follow this link, they have replaced the matrix factorization with a MLP layer, that is a multi-layer perceptron. So you can say that the general matrix factorization is a special case of neural collaborative filtering. So this is a more general collaborative filtering, a more general matrix factorization than a simple collaborative filtering. So I'll just get started and just as usual importing the libraries. This has been referred from the Keras. If you see this link from the Keras documentation on collaborative filtering, just in the modeling part, I have added a more MLP layer so that it becomes neural collaborative filtering rather than just a trivial collaborative filtering. So yeah, moving on. After importing the libraries over here, this part is just for fetching the data. That is the movie lens data set. It is again a famous data set. If you Google it, you can find that easily. Once that is downloaded, even this recommendation system consists of two data sets, just like the previous one. So naming this as DF, this is the first one. You can see it's a very simple, clean, and um, a very tidy data set. The first column is user ID, the movie ID, the rating, and the timestamp. So the first row can be interpreted as a user with user ID 1 has watched a movie with movie ID 1 and rated it a 4 star. So rating is from 0 to 5. So yes, that is it. And in this cell over here, I'll just tell you the logic what we are trying to do in this cell. So now in this existing data frame, and the timestamp feature is one that we'll ignore in our rest of the workshop. So that is not such a useful feature in this case. So I'm just going to append this existing data frame with two more columns, that is the user and the movie. So you see that I have modified the data frame with two new columns, user and movie. Now, what are these columns? I'll just let you know in a bit. So over here, the first line you can see is I have just collected the unique user IDs in a list, because you can obviously a single user has watched multiple movies and he has rated multiple movies. So just to get the count of the user IDs and to get the unique users who are present in the scope, I've declared a user ID list and collected all the user IDs in that. And next I have declared a dictionary. So if you look at the code, this dictionary basically, I have named it as user to user encoded. And this dictionary holds the information of the mapping user ID to its index in the list. That is, the key is the user ID. So for example, over here, user ID 1 would be the key and its value would be the index in the list user IDs, user underscore IDs. So maybe the first entry of the user to user encoded can be key would be a user ID 1 and its value would be 0 because that is the index. Since Python follows a zero based indexing, that would be the index of that particular variable. And similarly, I have defined user encoded to user. That is again a dictionary, just the reverse of the previous dictionary. That is, in this case, the key becomes the index and the value becomes its ID. Now, why am I doing all these things and will this be required or is this necessary? Is just a kind of programming style. And where exactly does this get used? We'll discover that in the later course of this workshop. So similarly, I have done with the movies. I have fetched the unique movie IDs and stored it in a list with the variable name movie underscore IDs. I have declared a dictionary with movie to movie encoded, and that is again a mapping with the key being the movie ID and the value being its index in the list, that is movie underscore IDs. And then I have again declared, so we are following the same pattern as the users. So we have again declared a variable movie underscore encoded or encoded to movie, and it is basically the reverse of the previous dictionary. That is, the key and values have been reversed. And then I have declared a new column that is user, and that is basically the dictionary user to user encoded. So what does this dot map do? That it maps with each user ID the the value of the dictionary. So for user ID 1, the key that is in user to user encoded, that is key 1, it will map its value 0. So now in this particular data frame, we have got all the information from the variable, the dictionary that was created. So the user ID 1 has an index 0, the user ID 1 again index 0, the user ID 2 would have be having index 1. So in user column, it would be 1. And basically this is used for some kind of mapping that we will make use of in the later course of this workshop. So yes, moving ahead now. Over here, I have just collected the length of number of users, number of movies, printed that out. So you can see there are 610 total number of unique movies, 9,724 number of movies, 610 users. Minimum rating has been given as 0.5 and the maximum rating has been given as 5. We have also converted the rating to float because we would be doing a min-max scaling. So as you know, for better convergence, especially in neural networks or regression-based problems, any optimization technique, it is better if we scale a numerical feature in the value from 0 to 1 so that the convergence becomes faster and also it becomes easy to converge. So in the next cell, I am just doing that what I mentioned. So if you can see the third line of the code, I am basically doing a min-max scaling. So this is the formula for that. And the rating, if the rating variable has now been scaled from 0 to 1 rather than from 0 to 5. Obviously, you can, scikit-learn provides a inbuilt package that is, I guess, min-max scaler for this function. So you need not do all this manually. You can just import the function and pass the entire column as an argument, and you will get the same result as it's done over here. And next we are doing in this cell is the random train test split. So first I have sampled the entire data set so that it becomes random sampling. And I have stored the values that we will send for training is just the column user and movie. That is the column that we created, the user and movie, that is index based column. Again, you can use any column. You can even use user ID and movie ID, since basically these are just IDs and these numbers don't convey anything important rather than the fact that we would be using them for the mapping, just to know that particular user, because it will rather learn the mapping with rating rather than the actual user ID or movie ID. So we have used that user and movie column and converted to a NumPy matrix. which is done by this dot values. So these two columns have been converted to a numpy matrix of two columns, and the number of rows is the length of the data frame. And then we have used, if you see the second last line of the code, we have used 90% of the entire data set as the training part and the rest as the testing or validation part. Again, for this entire exercise, you can use scikit's inbuilt function of train test split that takes care of randomly sampling the data frame as well as dividing into the training and testing part. Over here, we have done this manually, but again, it's not required. You can do that using scikit-learn as well. So these are some basic chunk of codes that we have written. We have obtained the final train and test part, that is the X train, the Y train, and for the validation, we have got X val and Y underscore val. So the X train matrix, if you see the shape of it, it contains the number of rows is the length of data frame and two columns. The first column corresponds to the user, that is the user column of the data frame, and the second column of the matrix corresponds to the movie. Similarly, the Y train shape is a vector of the ratings that have been scaled down from the value of 0 to 1. So next comes the chunk of this workshop, that is defining our model and the model architecture. So before jumping into the code of defining this model, I will just show you the architecture so you get an intuition of what exactly we are doing with this collaborative filtering. So now, since you have become familiar with the data set and how this data set is being passed into the model, I'll get you acquainted with the actual model. So you see that the model will get two inputs. The first input, one of the inputs would be the user and the other would be the movie. So you can visualize is that as we have created the xtrain variable, the matrix, the first column, that is user, will pass on to the one of the input, and the movie as the second input, that is input 2. Now we pass, so for example, first user has been passed as input 1, and the first corresponding movie that has been watched by him has been passed as the second input. They both get passed to their corresponding embedding layers. Now what does the embedding layer do? It basically transforms that particular user into a latent space of features. So over here, you can see that we have transformed it into a 50 dimension vector. So each user and each movie corresponds to a 50 dimension vector in a other latent space of feature space. And next we do the flattening. Now this flattening is just for mathematical purposes, because if you see the shape output of the embedding layer is 1 cross 50 and 1 cross 50. That is same as defining a 50 dimensional vector. So just to get it in place as Python treats it a dimensional vector, we just flatten it. So instead of 1 comma 50, it's just 50. And this is done so that the resulting dot product is a single value. So next, after the flattening, you see that we have done the dot product of the two vectors, that is the user and the movie, and then we get a single value. Up till here, that is till the dot layer, it is basically a simple collaborative filtering. That is what we have done in these particular layers is nothing but general matrix factorization. So one matrix is the user matrix. Each row is a 50 dimensional latent representation of that user, and the number of rows of that user matrix will be the number of total users. And similarly, there is a matrix for movies where each movie corresponds to a 50 dimensional vector, and the number of movies represents the total number of rows. And then for each user and each movie, there is a dot product, and that dot products, maybe you can think of some kind of um, similarity or some kind of interaction that provides with this dot product, and the output of this dot product can be used, maybe passed through a sigmoid. So if it's a zero, if it predicts a zero, you can see that no, this is not a there has been no such interaction, and if it's a 1, then there has been an interaction between that particular item, which in this case is a movie, and that particular user. But we are going to extend this idea of general matrix factorization, and after this dot layer you see that I am passing it to a multi-layer perceptron. So the output of this dot layer gets passed into a dense layer, and we just blow up the dimensionality by 150. So a single value gets blown up to a 150 dimensional vector. Again, that gets reduced in the next dense layer from 150 to 50. So this is just to create non-linearities, because we would be using activation functions. So simply how a neural network works. And the output would be again a dense vector with single value. So the idea remains the same, but in this case, since we are doing an item-based collaborative filtering, we will not modify this use case as a classification, but a regression task. So since we have the target as ratings, the final output of this dense vector would be something from 0 to 1, and we would try to match to the actual ratings, that is against a scaled down version from 0 to 1. So we can treat this as a regression problem where the target is the ratings and we are trying to predict those ratings for each user movie interaction. So yes, this is basically the zest of the model and the core chunk of how the neural collaborative filtering works. I will also reveal some more details about this in the at the end of the workshop. But before that, let me just quickly glance over the code, like what exactly I have done in defining this model. So we have defined the embedding size as 50, that is the 50 dimensional latent feature space. And second, user inputs is the input placeholder defined for the user. By the way, I'm using the functional API of the Keras model. I guess most of you would be familiar with that. If not, then you can look into the documentation of how a functional API works, just like a sequential API, but it has some advantages, gives you more flexibility. So in the embedding layer, that is we call from that Keras layers function, we pull in the layers dot embedding, and the first argument is the number of users. So you see that the number of users was something around 610. So what basically the embedding layer does, it creates a lookup table with 610 vectors, where each vector will correspond to one single user. And what will be the dimension of that vector? That is given by the second argument, that is embedding size. And we have kept the embedding size as 50 as per our convenience. And then are the rest of the optional arguments, that is how do we want to initialize. Since Keras by default randomly initializes, we just give an argument that there's a heap normal, we initialize the weights by that, and then put an L2 regularization. And we call this on the user inputs, and then we just flatten it because it creates 1 comma 50, as you should have seen in the diagram. We flatten it so that it creates a 50 dimensional vector. If you don't do this, then you will have to do some manipulation in the matrices so that they correctly do the dot product and give you a result of a scalar, that is a single value. So this flattening is just for that purpose. And similarly, we have created another input for the movies. Again, pass it to the embedding layer. Number of movies is the first argument. So it creates a lookup table of number of movies, and each vector corresponding to a 50 dimensional size, since the second argument is embedding size, which is 50, and rest of the arguments are optional. And the next layer, that is the dot product. This is how we define. In Keras, you have an inbuilt dot layer which computes the dot products. So this is how I have called layers dot dot. And in the argument, I have provided it the two vectors, that is the user vector and the movie vector, since these are the two vectors that will be used for calculating the dot product, and axis has been one. There are again different ways of doing this. You can also import a lambda layer from Keras and manually do the dot product function, write a lambda function of computing the dot product between the two vectors and then pass on to the model, or else use the inbuilt dot layer provided by Keras. So there are multiple ways of doing this. And up till here was the collaborative, the matrix factorization part. And then the output of this dot layer in the next line of code, as you can see, has been passed on to the multiple dense layers. So dense 1 with 150 neurons, dense 2 with 50 neurons, and the activation function has been kept as ReLU. And then the final dense layer, that is the output dense layer with a scalar, that is one single neuron, since we want to predict one single value, and that is the ratings. So over here you can see that, yeah, dense 3 is the final output of our neural network model. Now we create the graph of the entire model. So that is again from Keras model. So it has been imported earlier, and we pass in the input and output. So you see that we have passed a list of two inputs because there are two inputs to this model. The first is the user inputs and the second is the movie inputs, as we have created these two placeholder variables. And the output is the dense 3, that is the final prediction, rating prediction. Next, we compile the model. Optimizer has been used as Adam. This is the most optimum optimizations available nowadays. You can also use SGD, that is stochastic gradient descent. You can add a momentum to it, but why not use Adam? And the loss will be mean squared error, since we are treating this as a regression problem. We have to predict the actual um, prediction. So that's why we are using mean square error. And the last line shows the plotting of the model. You can plot the model to see the architecture. So just quickly, once again, since this is the most important part, I'll just quickly once again go through the entire model. So these two are the inputs. They get mapped into an embedding space. We do the dot product between these two vectors, that is the user and the input, user and the movie, to get the interactions between them. Then we pass on this scalar to a MLP, multi-layer perceptron, and the prediction will be a single value that corresponds to the um, movie rating. So during the training phase, it will compare to the actual movie rating. Then it will calculate the loss using the mean square error loss that we have passed in. Then it will back propagate and so on. It will do the training. So what I have mentioned, that is done in this next line of code, that is the model.fit. And we are the two inputs that we had passed. Remember, we had created a X-train matrix. So as I had mentioned, the first column will be the user vector. The second column will be the movie vector. And these two gets passed. The Y, that is the target, is the predictions, that is in Y train. We have then we have defined a batch size of 64, and we have run this model for 10 epochs. Now I have run 10 epochs for simplicity, and you can see that the loss is still decreasing. So maybe you can increase the number of epochs and plot a cross validation just to see at what time there you can see convergence. But for simplicity and for this workshop, I've just done till 10 epochs. And I've just passed one dummy. For example, we want to see the fifth user. So I have passed in the X train 4, X train 4, and the movie corresponding to X train 4. And I've used model.predict. So it gives me a prediction of 0.77. So that is the uh, rating. So once this is the main part of the entire thing, once this has been trained, the later part of the workshop, just the later part of this code just focuses on how to do the mappings that we had created earlier. So now comes the second data set, that is the movie data set. So if you see this data set, that is movie underscore df, it is basically the movie IDs, the name of the movie, and the genre of the movie. So collaborative filtering is not a content-based filtering, which we had looked into the first workshop. So we do not make use of these genres. We just use this for the like the output. But you can see, you can read more papers about hybrid recommendation system where it uses both collaborative filtering as well as it will use genres as a feature to do some content based filtering. So yeah, so moving on, the next cell basically in this, I have just created a data frame that is movies watched by the user. So the first line, I'm just randomly selecting one user from the data frame that is df.userid.sample. It collects one user. So in the next cell, you can see that that user ID is 49. And then I create a data frame uh, so for that particular user. So df, you can see df and df dot user id equal to user id. So it will result in the data frame where the user id is 490. So in the next to next cell, you can see I have just printed a head of that user id so that you can get a glimpse of it. So all the user IDs 490, and these are the movies that have been watched by him or her and the corresponding information. Next, we are also interested in creating a placeholder for movies not watched by the user. So this is done so that we make sure that we only recommend movies that have not been watched by the user. So the logic used over here is that in movie df we have you see this tilde basically represents a not function. Again, there are many ways of doing this. This is just one of them how we have done it. So we have selected the movie ID column and we have seen selected those movies which are in the column movie watched by user and then done a not of it. So you will better understand this if you are yourself trying out this code, and obviously there are different ways of doing this. And once I have done this, you can see this is the movie IDs that have not been watched by the user, and this is the data frame that has been watched by the user. And in this next cell, what I have done is I have done basically an inner join between the movies not watched variable and the movie IDs from the df table. So this is just to make sure that the movies are actually part of the scope. That is, there could be some movie IDs in this data frame that are actually not part of the training file, so we are removing those movie IDs. And this is how this is done. Create a set of movies dot not watched and intersect with it. Remember, we had created one variable movie to movie encoded, get its keys and do an intersection between that. Again, there are many ways to do this. You can do a inner join between the two data frames, or you can do this. So next, the next lines of code are just basically for the mapping. So this movies dot not watched index variable is to get the indexes of those movies, because this movies dot not watched variable contains the movie IDs. We get its corresponding indexes. Similarly, we get the index for user encoder. Remember that the user ID was 490. Its corresponding index is 489, since Python has a zero-based indexing. And then and why are we doing this? Because we want to predict on this data set. So we have are basically creating a prediction data set. So over here we have just horizontally stacked. So the first column contains the user encoder, and that is 489, 489, 489. It will be repeated until till the length of the movies not watched. So the first is the indices of the user, which will remain same for the same user. It's 489. And second column contains the list of movie IDs, that movie indexes that have not been watched by the user. So we will predict on this entire data set, that is user movie array, passing the same zero and the first column, flattening the results, and we get the rating predictions. So over here you can see that we have got the array of predictions that basically corresponds to the ratings. Now what I'm doing is I am sorting these ratings, because supposedly we want to recommend the top 10 movies as per his taste. So we will sort the indexes of this array with the highest rating. So for example, if point 0.9 is the highest rated, that will come first, and the top rating indices will contain its index. So you can see that we are using .arg sort and not just sort. So it will sort the array and it will return its indices rather than the actual ratings, because basically we are interested in the indices. And why is that so? You will come to know. So over here for each rating in the top rating indices, I have fetched, remember the variable movie underscore encoded to movie. So I'm using the dot get, and I'm passing the key, which is the index of that particular movie, and then it's returning the value, which is the movie ID. So hence the variable name is recommended movie IDs. So basically it's the list of the movie IDs that should be recommended to the user. And this cell just shows the movies that have been watched by the user. So you can see the movies with highest ratings that have been watched by the users are so and so. Three colors, red, blue, and this is the genre. And now we print our predictions. So the top 10 predictions, and you can see that these are the predictions that have been given. So these are the recommendations basically. So the movies like Outbreak, Blade Runner, these are the movies that have been recommended. And from the genre, you can make out, like, since these are drama, romance, mainly drama, romance, these movies have also been recommended. But just make sure that these genres as such explicitly have not been used in our modeling, because collaborative filtering doesn't do a content based filtering. So we have not used these genres as such. It's just a matrix factorization that we have done. Maybe you can come up with a hybrid. There are some hybrid recommendations that are being used in real life. So in real life, for Amazon example, it doesn't use a simple collaborative filtering. So yes, this was the basic zest of neural collaborative filtering. Now, one important point that I want to add is the model architecture that you have seen over here. You might have realized that this is a bit complex demo that I've shown, and you will have to go through the code yourself to get a better idea of it. So just to keep things simple, I have used a very simple model architecture, whereas exactly it's not as simple as shown over here in the actual paper. So if you go to the actual paper, or go to some blogs associated with that paper, for example, search on Google, neural collaborative filtering implemented in Keras. So you will see that the model is actually a little bit more complex than this. So basically, there are two parallel tracks of input and user. Then there is parallel tracks that have been passed to the MLP, and there are one track that has been kept intact. You will get the details, but you can use the entire this code as it is and just add a couple of lines more in this part to make the model architecture exactly as same as the one mentioned in the paper. And it's not a very difficult thing to do. You just have to add some more layers and just keep track of those. You will get to know when you go to the blog post and see.